Whew. Okay, so I have some uncommitted changes apparently since last time. I think maybe I did something off stream. I don't remember. But I guess this makes sense. I guess. I guess I can. So I can take a look at what the state, I guess, of the game. So this is the game right now. We can move around and jump around and stuff. Yeah. So before I had some controls. I could like move up and down, but that doesn't make sense anymore. Because we have gravity. So I can only jump with space. So we can remove that. What else? I changed some speeds, changed the gravity. I added. Okay, actually, I did some mock-up stuff. I think I will remove this. Will not need that. Okay, makes sense. Hello. Yeah. Okay, let's commit that. Small stuff. Okay, so there is somewhat of a big problem right now. Let's see. Oh no. Wrong tab. Oh. Ah, that's cool. That's cool. Is that? Do you have a job right now doing programming, or no?
DJ my side, DJ my side, DJ my side, DJ my side.
But that's awesome. That's nice. Ah, nice. Well, good luck on that. Oh shit. Okay, so I have this game where I can jump around, I guess. So we are this rectangle, and the world itself is represented as a bunch of triangles. So the only collision test we have is colliding a rectangle against a triangle, and we just do that for every triangle in the scene, right? And the thing is that the way we render this is also triangles, and right now that's all. It's completely hard-coded. So I write out this triangle data twice, basically. So one time I do it for the actual rendering, which is here, and they have colors and stuff, right? And I do it in a different place also for the collision. So it's kinda duplicated, because I could like change this. I guess let's change this to 0, maybe. Like I have to keep this in sync. Okay, that's not the best triangle to change, but I mean, I basically have to keep this in sync. So what I basically want to do, I want some format that's kind of nice to edit, and have that basically generate these triangles for me. And I think a nice way, and I'm gonna, because I want to make a level editor at some point, but I'm gonna just focus on the data first. And I think one nice way to represent these kind of things that we want to triangulate is by some... I mean, we basically want to define some kind of polygon, right? With a set of points, I guess. So this would be 1 point here, in this example. 1 point here, 1 point here, 1 point here, and this one isn't even needed, right? We can just put a point here and 1 point here. And these triangles should be generated from those points. And I guess the first question then is, like, how do you actually... So I guess it would be some kind of list of points, and I think like the order in which they're placed is gonna define the surface. So this is gonna be the first one, and this is the second one, and so on. Like, it can't just be random. It can't be that this one and then that one and then this one and that one. That's gonna look all messed up. And I think so we need some kind of triangulation method, and there are a bunch of these actually. And I think we can focus on doing a convex hull triangulation first. Maybe I think that's simpler at least, and you can probably adapt it to work on concave shapes later. So let's do some research, I guess. Yeah, the Luni triangulation. I've heard about this before. I wonder if it's simple to do. Oh yeah, there's a lot of research on this. I mean, I do want to be able to create shapes like this, right? And maybe that is a completely different method. But if I remember correctly, you can also like pre-process this shape kinda to split it up into multiple convex shapes. So I guess in this case you could put an edge here, and this would be two individual convex hulls. Then you could run some convex hull triangulation on those two separately. I think that's a method that makes sense. Okay, so we want a set of points that define the convex hull. We're not even gonna have points inside of it, so we just want these edge points. Okay, so they discuss actually generating the hull, which is, we don't need that. We don't need that. Okay, so that was, okay, so this was for creating a convex hull. I want to triangulate it, and I guess we'll look at this, the Luni triangulation thingy. I have not done lead code stuff actually. maybe a very long time ago, but not really. Not really. Well, yeah, I'm not sure. Maybe I've like found like if you try to create like a game or a game engine, then you will find those kinds of problems. Those kinds of problems yourself, I think, and like find ways of solving them. I am 27. So where is the actual algorithm described? I mean, the algorithms for computing the lunar triangulations rely... okay. Well, maybe I should read this first, I guess. Into triangles whose circumcircles. Okay, so that's the point. That's the circle that is defined by... that intersects all 3 points of the triangle, right? I guess. The lunar triangulation of a set of points is the plane or is the triangulation... I'm not quite sure I understand this completely, but okay, we need a robust and fast way to detect if point D lies in the circle of A, B, and C. All right. There's gotta be other methods, right? Like, what did I search for? Convex hill triangulation 2D, right? Yeah. Like, is this the lunar triangulation the only thing? Like, I've heard like about like air clipping triangulation, but like, why is it so hard to find anything? Like, the lunar triangulation can't be like the only way. Like, I don't care about the proportions of the triangles either, not right now, at least. Oh, a classic problem. Okay, it's exactly my problem also. I want to define... Yeah. This is exactly what I want, I guess. Okay, this seems sensible, I guess. This seems very sensible. So I guess we can read this maybe, or find something that's not as academic that describes this. Aren't you bored of coding all day? Actually, well, sometimes I am. But I mean, it's work. Well, this is not work, but I do work as a programmer, so I mean, I don't have a choice. But it is actually fun, I would say, especially working with games. It's pretty rewarding, and work games. There's so much to do, like different kinds of stuff if you're making a game. Okay, so what was the description here? An ear of a polygon is a triangle formed by 3 consecutive vertices. Okay, makes sense. For which the middle vertex is a convex vertex. At such a vertex, the interior angle at the vertex, okay, interior angle is smaller than pi radians, and the line segment lies completely inside the polygon. Well, what does completely inside mean? What does that mean, really? Like, okay, the line segment from the first vertex to the last one lies completely inside the polygon.
We trust each other.
Well, I don't. Oh, okay. Right, makes sense, I guess. Because it could be, I guess, that that this point could be here, right? And then this line crosses that line. But how would I check that? How would I check that efficiently? Well. I guess we can, like, doing this air clipping, like removing one triangle at a time. That feels very reasonable, and just going around it in order. Alright, yeah, this 0, 0, 1, 2 triangle is would not get clipped. Okay, I mean, that makes a lot of sense, this algorithm, actually, I must say, to me right now. So what we want is yeah, what do we want? We basically want I guess we want to represent our world as some kind of collection of polygons, right? Maybe I can call it the editor polygon. Or an edit polygon, I don't know. Okay, so this polygon is only... It's only going to have a list of positions. Well, like the... Yeah, it's a list of vertices, right? That's all there is. And for now we'll do this very, very easily and stupid. We'll just have that as a fixed number of... we'll limit it right now to make it simple. So we'll have the actual count in here as well. Okay, so we have some polygon. And for now, let's say that we have one polygon. So we have a single polygon in the world, which we do have right now. We can consider this whole ground as one polygon. So, all right. So we can initialize the vertices of this polygon. So if we want, I want to recreate this one then. Yeah, let's do that. So we can say that let's make this one vertex 0. So 0, 1, 2, 3, 4. We'll need 4 vertices to define this shape. Okay. Position. Maybe we can call that vertex. Yeah. Oh, did I make that? I make that a 3-dimensional vector for some reason, but we are working in 2D. So let's see where we put these. So the first one is at minus 5x, minus 5. And I think we moved it up by 1 unit. And this one in the middle, I think that's like the origin of the world, so 0, 0. And this one is at 5 there and 0 still. Yeah. And this one is still at 5x, but we moved it down by 1, I think. And this fourth is minus 5 and minus 1 downwards. That should be correct. Okay, so we can add some way of visualizing this polygon with some debug lines. Let's move those here. So editor polygon. So we want to draw a polygon, right? That should be really simple, because the polygon has some vertices, right? We go through every vertex, yeah. And we want the other, the next vertex, like so, and we have to wrap that, because if we're at the last vertex, the next one is the first one, right? So we just wrap that. So we have those two indices. Oops, vector. So we have these two vertex positions, and it should be easy to just debug, render those. Okay, so that's for each vertex, that's a single line now, right? Yes, yes. I think that should work. So let's replace this one for now, and we will just draw our polygon and see how that looks. Doesn't quite look right. What's going on here? Did I set the positions incorrectly, or wait? Wait, 4, 1, 2, 3, 4. It's 5. It's 5 vertices, right? But are these correct? 5, 0, 5, minus 1. It looks fine to me. Yeah, that was the only problem. Okay, so we have this shape. Well, actually, okay, it's a bit more up, actually. I think it's like 0.1. Yeah. Okay, so we have this polygon that's just defined by these points now around the shape that we want to create. All right, that's good. And now I guess we'll just need some okay, yeah, we at least need some function that just generates some list of triangles now. So we need a list of triangles that define this shape, right? We want to convert the outline to a bunch of triangles. So I guess we want every triangle has 3 vertices, right? And I think it's nice if we just define those, like the triangle will point to the location within this polygon of the vertices. So something like, let's call it just triangle, I guess. And every triangle will have a list of... I'm not sure if I want to make this an array or... let's make it an array. So each triangle points to 3 vertices inside of this. Yeah. So we want to triangulate. Is that the word for it? Triangulate? Triangulating is like when you locate someone, like by measuring their cell phone signal, right? But it's called triangulation in this context also, I guess. Okay, so we want to triangulate a polygon, and we will get out some number of triangles from that. And we also are. It's also good if we know when calling this, like how many triangles were actually created for this polygon. Right. I really want to call this. Okay, whatever. So okay, that's all. So we'll have some let's call that the full name. All right, I can try to just do this method then. And like checking if this line segment lies completely inside the polygon. That's not trivial. I will just skip that right now. But I think it will work anyway for our basic shape, I'm pretty sure. So what we want to do is basically it's the same. We want to go through every vertex. However, now, and we want to find the next vertex also right now, the exact same way. I can call this P. Too much to write. Type. Okay, so we find the next vertex and then the next one after that as well. So then we have three. We have 3 points then, which, yeah, that just is a triangle, right? I picked 3 points of the polygon, and I guess I actually have to implement this check actually, because if I just do this and pick this triangle, that's not gonna work, because this is the first one, this is the next one, and this is the one after that. So the triangle will be it will go like this on top, which is completely wrong. So I guess, but I wonder how I should how to add this check. Maybe they mentioned that. Okay, for each vertex. Oh. Okay, it's. Wait. For which V a convex vertex. What's a convex vertex? What's a I guess a convex vertex, I guess. Okay, that should be trivial. Because if we say that the polygon has to be defined, like by ordering the points in a clockwise direction, which we did right now, then it should be trivial to check like which if this is buckling inwards, right, which it is in this case. I think that should be pretty easy to check somehow, because we should be able to check the Yeah, we want to check this angle. And how do we actually do that? How? Trigonometry. How do I? Like I have two lines, right? And I just want to find the angle at where they intersect. I feel like that should be very easy, but should be very simple. But how? It's definitely trigonometry somehow. We're at least gonna need the points. So these are the 3 points that make up the triangle. And we need to find the angle. It can't be that hard. Actually, we can also debug draw this. That would be nice. So if I draw some kind of point at each vertex. So let's say this middle vertex is the one we should visualize. With P1. Is convex. So let's say if it is convex, we'll do green. Wait, that's green. And if it's concave, we'll make it red. So now we just need to implement this. Yeah, this botsman, I don't know how to wait. Do I just? I mean, surely I am a moderator on my own stream, right? But how the hell? Wait, I have Chatterino. No spammering. My Chatterino login expired. Oh, oops. Like I don't know how to to ban people. Wait, do I just click like his Oh yeah, there it is. Okay, I found it. I just click his name. Okay. I just click his name. Cleaned up. Oh yeah, I can probably do that as well. Oh yeah, it is /ban. I was looking for like exclamation mark comments. But okay, slash. It's slash. Okay, so we want to check the convexity of this middle point. So how to do that? Well, let's just confirm that this works. We should see some, yeah, we see some points now. bit hard to see. I can increase the point size. Debug. Okay. That's better. So that should be a nice visualization now, to see if my algorithm is correct. But how the hell do I actually figure out the angle? I know that when you use this A-tan, I guess I have to include math first. Math.h A-tan 2f. But I think I should be able to just use the. So I want the two vectors. I want one vector that points from the first vertex to the middle one, and the other vector that points from the middle vertex to the last one of the of the triangle, right? So let's call that D0, and that's gonna be. Do I really not have this included? Okay, so we subtract P1 with P0 and normalize that. And D1 is going to be the point from P1 to P2 normalized. And now it's possible to get some kind of angle, like I don't actually like. I wonder what this like is mathematically, right? Like A-tan to F, or not F, I guess. Yeah. A-tan yx returns the angle theta between the positive x-axis and the ray from the origin to the point xy. Yes. But then the question is. If I do this twice for my two vectors, can I just subtract one angle from the other? Can I do that? I guess we'll see what happens. So it's y and x reversed. Okay. So we have angle 0 and angle 1. And I feel like we should be able to do something with these two angles. Well, they're always going to be. They're always positive. I mean, something like A1 minus A0. And what do we want to do? We want to check. Do we just want to check the sign? We'll try some shit. I can't fully visualize this, so let's try that. Yeah, that doesn't really work. Almost. It might have worked by chance. You know that I reversed it. Like, it almost works, right? This is convex, this is concave. But yeah, this is wrong. But yeah, I need to. I will ask my friend Chat GPT, I think. Let's see. Oh, you know him as well. Okay, how can I measure the angle? The angle... well, I guess I want to calculate the difference in angles. The signed angular difference, let's see if he can understand this. The signed angular difference of two vectors in 2D space. I think that's it. Because like you can use the dot product really easily to figure out how aligned they are, but I'm not sure like how, because I want a sign, and the dot product doesn't give me that, so I need something more. Wait, are you shitting me? That's exactly what I did, but that's exactly what I did. But it's... Oh, wait. To ensure that the angular difference is within the range... What the hell? Okay, let's... Maybe that improves it. Yeah, this is literally... But it's not working. It's not working. So let's try this thing then. So this is gonna be 8 tan 2 of the sine and the cosine of this. Okay, that works. Oh my god, I can't believe it. To ensure that the angular difference is within the range. Right, okay, I think I get it. Well, I don't get the mathematics, but I get that we have to do something with the value. Okay, that's literally it. Right, so now we know if a point is convex or concave. So these are all convex, and this is concave. So during triangulation we just skip this one. Or we skip the triangle that is defined by this vertex as the middle point. We skip that one. Right, so we can just copy paste this now. Copy paste. Okay, so now we know, like, if it's not convex, so if it's we just continue, literally, like so. When I'm not coding, I play games sometimes. PUBG or something like that. Still. And I play piano also. And I make music sometimes. Like digitally. Now I actually wonder, is this really... Well, right, we need some... Because we're as we do this triangulation, the idea is to like remove triangles from this original polygon, right? So when we do that, I don't want to change the original polygon. So in order to do this, I am going to keep a separate list. Yeah, right. So when we clip this triangle, they even visualized that here. We have to remove this 3 vertex from the active list that we are searching through. Right. That should be fairly simple. So that will just be a list of indices, of triangle indices. Let's call that. Let's call it the working set. And actually we have some kind of limit here, so let's define that somewhere. We have the max polygon vertices. Well, I think polygon max vertices. Let's say that. Let's say that. So we have the working set of vertices. And before we do anything, we just have to fill those out. And that's just that. So like an identity mapping of sorts. And then we need to keep track of the working set size, right? Which is going to be the vertex count to start off with, at least. And then this will shrink as we are removing vertices. And I think that when we remove this, we actually have to keep the working set the same order. We can't change the ordering of the vertices. Yeah, we cannot do that, I think. And that's a bit annoying, but it shouldn't be too bad. It would be nice to have separate some stuff into functions, but I think we can manage anyway. So instead now, so instead of going through every vertex all the time, we are going to go through the whole working set. we go through the working set, and instead of looking up these vertices, we need this in direction now. Yeah, we need to look up in the working set which triangle or which vertex this is actually pointing to. I think that makes sense. And then let's say that we need another we need to figure out whether we actually should split or should clip this triangle, which for now we'll hardcode that to true. And if we should clip the triangle, I guess we have to do two things. Well, if we clip it, we should output it. We should output it. Yeah. Let's actually start by initializing this to 0. So, we want to output this triangle, which... Okay, let's fetch these indices beforehand. So we have the index 0, 1, 2. 0, 1, 1, 2. Because these are the these are the indices of the original polygon, right? So these are the ones we want to write out. So that's it. So that's the triangle we want to write out, and that's just like that, like that. Okay, so that's fine. Except now we have to remove it from the working set also. And having that be ordered is a bit annoying, because if you want to remove an element from an array and you don't care about the ordering afterwards, you can just swap the element you want to delete with the last element, which is extremely fast. But in this case, I actually care about the ordering, so which means if I want to remove an element in the middle of the working set, I have to move every single element that comes after, like one step backwards, right? It's a bit more tedious, but so we want to, if we clip the triangle, we want to delete the middle vertex, which is J. Okay, so this index we want to delete. So how do we actually do that? I think it's pretty easy anyway. So I guess we'll start with. Need some name for this. Let's say del. Okay, so we start at the index we want to delete, right? And we want to go until go through the whole working set -1, like that, because we want to, and then I think it's pretty easy actually, working set. So we want to copy into the cursor. Maybe we can call it cursor. I'm out of short iterator names here. But we want to overwrite this value with the one in front. Yeah, so we're moving forwards in the array and just moving everything one step to the left. Mentally to the left. I feel like that makes sense. And then the only thing is to reduce. Well, we can do that first, I guess. So let's say we have four vertices. We want to remove one. Yeah, I don't know if that's more confusing or not. But sure, I think this should work. So that means we now removed this vertex from the working set. And I guess we can like, I guess there's some like kind of upper bound. You can probably calculate some kind of upper bound by knowing, if you know how many vertices your polygon has, there's probably some upper bound to how many triangles can be created from that polygon. But for now, let's also ignore that, because I mean there's a risk that we write too many triangles. If we have, let's say, so now we're actually going to call this function. So we'll have our triangles, and like this number, well, 256 is fine for now, I think. Did I make this a size T? I don't know. Triangle count. We don't actually have to do this. Well, yeah, let's do this here actually. So I want to generate the actual collision shapes now from our polygon, just to see if this is working. So we have the... Well, I can do this here. Or no, who cares? Who cares? Let's do it here. Okay, so we get some list of triangles here. And let's just go through every one of these triangles and that we get from the triangulation algorithm. And we want to add them to our collision triangles, or we want to, I guess, create collision triangles out of them. So just pull out these indices from the triangle. Makes sense. And then we have to fetch the position using this index. No, that's a vec2. So we have the position 0 and so on. So then we have the positions of the vertices of this triangle, and then we just pass that into this one, because a triangle collider, yeah, that's just a list of 3 points. Okay. Oh, I have to set the correct one, and the triangle count should just be the one we get out here. like that. Seems simple enough. And then let's add back the debug rendering of these colliders and see what the hell happens. Okay, oopsie. This is I have to take the address of this. That's pretty wild. It seems to be working. However, why am I colliding with this bottom one? Is the direction wrong? Maybe I should add back. I had some way of... I mean, this triangle looks really... pretty sus. Yeah, what is this? What is this topology? So I assume what happened, I guess. So we took this one, and this one. That's the first triangle. This is the first triangle. And then it moved on to this triangle. This is the second triangle. Makes sense. And we delete this. Well, yeah, we delete this. Okay, it does look fine. It does look fine. I feel like it makes sense. But why are we colliding? Why are we not colliding with this top triangle? Maybe it's just my collision code. I had some way of drawing the normals before. I think this is it. And yeah, that looks fine. Because I mean, these are... I can walk on this. And I can walk on this, but... Okay, this one is actually flipped. Yeah, it is flipped. But how can that be? The algorithm should always go... Well, since I define my shape... I define my shape to be clockwise. So that's I think every triangle should always be clockwise. Shouldn't there be a... I'm not sure I understand what the hell... It's just weird. Okay, I can change the topology a bit to make it a bit simpler to look at. So if I just move this point to the left a bit. So that's 0, 1, 2, 3. Move it to the left. Right, that's a bit better. Well, now there's obviously a mismatch now between what's being rendered and this, but this is the first triangle, and this is the second triangle. This is the third triangle. But what could be the problem here? I think I would see this problem if let's do the algorithm manually, I guess. So yeah, this is the first one. So that means we delete this vertex. That one is deleted, and the winding is still clockwise. And then this is the second. So we delete that one. Deleted. And then. Yeah, then we jump here, I think. And that should still be... It should still go through it like this. What's the problem here? So... Because I maintain the order of the working set of vertices, and so the triangle winding should always be clockwise. I feel like. Can I verify that? I guess I can check the interior angles, like the interior angles. Well, I want like the signed angle again, right? So, okay, I guess I can ask ChatGPT again. So I just want to verify that the order I define the vertices inside every triangle is clockwise, right? That the wind, I guess, it's like the winding. Order of a triangle defined by 3 to the points is clockwise. The determinant. Okay, interesting. The determinant. Okay, so if I calculate the determinant of the triangle, that should be enough then. Okay, and the determinant is One, two, three. Okay, that's confusing because I start on with 0. So x x y y. Okay, and that's 2 3. Yeah, 2 3. Plus 3 3 1. So 2 0 2 0. I think maybe I can format this a bit nicer. It's like this, right? Times 1 2. So 0 1 0 1 0 1. That's the determinant. Okay. If the signed area is positive. Okay, so I want. I think I want it to be clockwise. So the determinant should be negative, like that. And let's see if that crashes. I really think it should. Or it should assert. Yes. So we do have one triangle that is counterclockwise. That's interesting. And I guess the easy fix is to just, if you just swap 2 of the indices, that's fixed, right? That fixes it. I think. Yeah, that fixes it. So that's, I don't even have to debug this. I think let's just try that. So if the triangle is counterclockwise, I can't just. I would have to refetch these if I swap the order. Maybe I just do I need the indices later? Yes, obviously. Okay, I write the triangle using those. But let's say that we can swap these. So we have the temp, which is so we can swap. Does it matter? Okay, we swap 0 and 2. I think that makes sense. So we save 1, we overwrite 1, and then this one is temp. Right. That's how you swap 2 values. And we also swap the positions. Otherwise, this is gonna be bad. Okay, so we swap the indices. We essentially swap the. We flip the triangle around. That makes sense, right? And we could recompute the determinant, but is can I? Oh god. I guess I can remove the gravity for testing. Wait, what? Is oh, will I do some lead code problems? I don't know. I don't know. I don't know if it would be fun to me. Cause like it's so, I guess, isolated, right? You just get some problem. Maybe it can be fun to challenge yourself, maybe, but just solving problems for the sake of solving problems doesn't seem so fun to me. So how did I... What's wrong? What's wrong? Okay, so that's... How is this messing it up? If I swap the two positions... let's just, I guess, try to do this just in case I completely... Oh, so let's refetch this now that we reordered the indices. Yeah, that's broken. Like, but why? So it seems like, I guess, the triangulation just doesn't... It doesn't output anything, but... What could possibly be the problem here? Like, I saved 0 so I can overwrite. This is how swapping works, right? I didn't... Yeah. I think this is how swapping works. So, I'm swapping the indices. How can that possibly not work? Is it the other way around? Oh wait, I should check this first. I guess, right, I should check that first before even caring about this. I think that makes sense. That might be one issue. I'm completely... I guess let's see where this actually fails then. So let's actually assert that it... Oh wait, it should be checking positive, right? Wait. Right, if the determinant is positive, then they are counted. Okay, I should check if it is positive. That makes a bit more sense, hopefully. But it still doesn't change. Wait. There's... There is no triangle here. There is no triangle. Oh, wait. What? All right, of course. Wait. Of course. I guess I basically... Right, this should be completely different, basically, kinda. So we want to keep finding triangles, right? As long as there's at least 3 vertices in the working set. Right, and if there is... Yeah, if there's 3 vertices... we should find that one. Okay. So... Then I guess the question is... I guess I still need to, I guess, go through the working set anyway. But we just need to do it more times, right? We just need to do it more times until all triangles are gone. That was the problem. Kinda obvious, now that I think about it. Okay. So now I guess this determinant check actually does something, right? Well, what? It doesn't. That is interesting. Well, I'm not gonna complain because it is working now. And let's add back gravity. Oops. Okay. That is nice, actually. So now we can, or we do, we just define our world as this set of vertices in a polygon, and I guess we can just now we should be able to pretty easily make this a bit more complex, let's say. So we can add a new vertex 0, 1, 2. Wait, 0, 1, 2. I guess let's we can move this back first to where it was. Okay, very nice. Let's try to add something that goes out here as well, and that is vertex 0, 1, 2. So after vertex 2, right? So after vertex 2, let's insert a new one. That's maybe 10, and let's say minus 0.5 or something like that. And now we have 6 vertices. We can actually, when I create the world, I create it 0 initialized? Yes. So let's do that. So now we can add like arbitrary That's cool. Looks like a spaceship. Looks like a spaceship. And I mean the quality of these triangles can definitely be improved, because it's not really ideal to have these extremely long triangles, right? It would be ideally be better to create a split here, right, and have this be one triangle, yeah, instead of having right now 3 triangles that are like extremely stretched. But it at least works. That's all I care about right now. So that's cool. Okay, I think the next step then is to actually also use the triangulation to generate this stuff that we render. Yes. And for now, like this grass here, that's actually because I wonder if I can do wireframe actually in my pipeline. Create pipeline. Yeah, create graphics pipeline. So this is the world pipeline. I think it's somewhere in where could it be? Rasterizer it is. So we have a, well, do we not have the fill mode here? Is it, no, it's not polygon mode, right? Well, where is it here? Where is the wireframe? Vulkan wireframe. Cull mode. Oh god. Surely there is a fill mode in the Vulkan pipeline, right? Or VK polygon mode. Okay. Rasterization. Okay, so what? It is the polygon mode. Did I just miss it? Okay. Okay, right. The topology. Okay, interesting. Topology is still triangles. Okay, let me hide the debug rendering now, because we can be pretty certain that the collision shape is fine. And let's hide the polygon as well. So yeah, the way that this grass works, I use vertex coloring right now, so there's no texture or anything, but I just basically just subdivided this mesh myself, right? And for now, I'm gonna skip that completely. I will probably add that back later to add some kind of detail, right, to the edges. But for now, I'm just gonna take the triangles, exactly the triangles that came from that we're using for the collision as well. I will use those for rendering right now as well. This actually looks super cool, actually. This wireframe view of the flowers. All right, but I think it should be pretty easy. Well, at least we will see about that, I guess. So right now we have this code that creates these. Well, hold up. I'll remove this first, so we can see it properly. Right. So we want to get this grass right now, and yes. Okay. So we have this code right now that actually creates these triangles that we use for rendering, and we also we generate these flowers, right, which I still want to do here, but this actual like level geometry I want to get from the triangulation of the polygon. Right, so I think we can add as input here, I guess for now, what did I call it, an editor polygon. So for now, we'll just pass the polygon. We'll pass the polygon in here, and well, I guess it would be ideal to just run the triangulation once. That would be the most ideal, but for now, yeah, just because the uploading of the actual or the field, the upload of the vertex data happens at a different place right now, but that's fine. That's fine. So we'll just do the same thing we did here. We call the triangulation function. Right. And for each triangle, we should somehow, so the rendering does use an index buffer, and for now it should be pretty easy. We can just, there should probably be some like base offset. Well, I guess we can take that into account as well. So this should be pretty simple. So we get the triangle. And just straight up use the indices. And well, yeah, we do want to do this. We want to, because if we already appended something, we should offset that index, right? Right, we appended 3 indices, right? And then right, and the vertices, those are just the vertices will just be, for now, the exact vertices that are sort of inside of the polygon. So the polygon has some number of vertices, right? And we will set those. Like so. Right, and then we add this, increase it afterwards. Okay, so for every vertex we just take the vertex that's inside of the polygon, at least for the position part. Right, we have to convert. Can we? Whatever. We'll take out the position, and then because the rendering is actually still 3D. Well, it is. We won't have some depth in the scene, right? But for now, this polygon doesn't have a depth really, so we'll make that 0. But so we copy the position from the polygon. And what more do we have? We have the position and the colors, right? So we have to set some kind of color here. And like also right now, the polygon doesn't have a color right now, or some kind of material, right? But yeah, so I will set that to just some value. I mean, we have the color. Here. I wonder which one it is. It's this one, right? Well, probably this one. That should be brown. Okay, let's see what happens. That works. Oh, and that's an annoying bug. Why is the player... What do I set the player position to initially? Maybe I should move him up a bit, but I don't know why... Yeah, okay. Okay, that's cool, actually. That's very nice. That's cool. And I guess now I could I could in theory try to procedurally spawn flowers on these parts as well. That could be cool. I think I will do that, actually. So in that case, we want some set of positions, right? On which, where we want to plant these flowers. And right now that's like done in a very simple way. It's just hard-coded between 0 and 5 on the x-axis right now. And I like know at which height the ground is also. And I just put them there. So I need something more complicated, but it's not going to be a lot more complicated, I think. I guess what I basically want to do is I just need to find every edge of this polygon and just pick some random numbers along that edge instead. Should be pretty simple, and I think the number of things we want to place should also be scaled somehow based on the length of the actual edge. But as a start, we can yeah, what we want to do is go through every vertex of the polygon again to find the edge. I should start using uints for these iterators because like it's always gonna be fine, the range, and it's shorter to write. So find the next vertex while we're looping through this, and we fetch those two positions. So those two define the edge, right? And now what I want is, I mean, I only want to spawn flowers like on the ground, right? Not on the ceiling. Maybe we can spawn vines or something like that that hang down later. But for now, I only care about surfaces pointing upwards. So we will have to compute the normal of this edge, and that is very simple. Let's take the direction vector first. We need that for the normal calculation. And the normal is just calculated by swapping these two. I think that's how I did it in. Yeah, okay, so it's a negative y, for some reason. Okay, so all we need to do, I guess, is if the normal is, well, yeah, let's say if the normal is pointing down, so that's just checking the y-axis of the normal, right? We just skip this edge. And otherwise, what we do is that we spawn some flowers, some plants, and let's keep the value fixed right now. So we have some kind of value here between 0 and 1, right? Randomly generated. And if we have that 0 and 1 factor, that's going to mean the relative distance, like the relative position along this this edge. So how do we actually map that to a position on this edge? We can just lerp. We can just lerp between these 2 points with the random factor. That should be it. And it is. Now a very slight problem, I guess, is that at this slope here, it might be a bit hard to see, but the bottom of these flowers and grass straws is they're still completely horizontal, so there's a tiny bit of a gap here. So I think I want to make those align to the surface, right? So I think what I can do is just easily pass this direction vector as well. So this direction will be pointing towards, I guess, where right is. Yeah, so this is towards the right. So I guess it's the tangent of the surface, basically. Right, it is the tangent of the surface. Yeah. So we have to pass those along also to our functions that actually generate these things. So I think let's skip this 0.5 multiplication to make it easier. So we have the width, and I think like the simple way, I guess, would be to just subtract both the dimensions by the width, and I guess that's all I have to do, right? So I scale this by the x component of the tangent, and I also have to add it to the y-axis as well, and we'll see if that's the correct direction and everything. 50-50. I think I got it right. Yeah, that looks correct now. Well, except for the flowers, right? Because I didn't change those yet. But that should be as simple. So in the flower function, we also have to take into account this now. Alright, so these are the top vertices, and these are the bottom. And we'll do the same thing here, actually. Like, just include this factor, 0.5, into the width. So this isn't actually the width, is the half of the width. But who cares? I don't need like an accurate width in units anyway. Like that, and then the exact same thing with the y direction. Looks fine. All right. I feel like the next step now, because this polygon is still defined by some in code, like it's hard coded, right? This level or whatever we're gonna call it. So the level is still completely hard coded, but at least it's just this now. Like this defines the whole level now. So if we want to make some kind of editor, right, we can, I think, easily do that now. Because all we have to modify is the data of this polygon. And we probably want multiple polygons in the future, obviously. Like platforms or, I don't know, something like that. Like parts of the level. But I think this is very nice. And we even have procedural grass already. So whatever polygon we make, like there's gonna be grass on it. I can also add some more stuff. So after the last vertex, this is the last vertex. So I can add, I guess, one more up here or something. So minus 10 maybe, and let's say 3 maybe. Yeah, that is pretty cool, I must say. And I wonder how many vertices these flowers actually take up, because we definitely need some kind of some budget, or maybe control it in some way. It's like 256 per segment right now. But how does it look if I lower it? Let's see. That looks... Oh, that does not look as exciting. But 256, I don't know how many triangles are per flower. I don't know, it's 1, 2... Wait, how many is it actually? It's 1, 2, 3, 4. It's just 4 triangles, and the grass truss is 3. So it's not that many. I feel like I think I guess we can print that. That would be fun to know. So after we filled the primitive data, we have some. Yeah, we grabbed the index count here already, so we can print that. Render triangle count. Well, what this is? It's a uint. Right, and we can output the world triangles. We can do it on the same line. So we have triangles and vertices. Like that. And we need the stud.io. Okay, so we have 5,500 vertices right now. Don't know if that's a lot or not, like relatively speaking. Maybe the flowers should be larger. Maybe I can make some different kinds of, like, so that cover up more area, I feel like. And we can make it a bit more sparse too, like the distribution is not that nice right now. It could be a lot better. It's completely just uniform, random. And I guess we can change. We could change that as well. So the actual number of things we want to spawn is going to be proportional somehow, right? To how big this edge is. So we want to know the length. We take the length of the edge and if we have some kind of density, I wonder what unit I should use here. Like we could say how many flowers we want per meter, I guess. Yeah, like approximately. Or we can have plant density. So let's say we want 10 plants per meter. So what does that mean? I guess that means that it should be pretty easy to calculate, like, so the number of flowers then that we actually want, or plants, plant count, is the length of this, because that's the number of meters that the edge is. Yeah, that makes sense. Like how many meters long times how many things we want per meter. I mean, that's it, right? That's simple enough. So let's try that. I don't know, seems about right, maybe. So if we want 50 per meter, that looks kind of fine. Looks good. What about 40? Looks nice. Okay, that is... I think that's very, very good progress, actually. So now we can completely define our scene, I guess, our game world, using polygons instead of this completely deranged, hard-coded triangle generation. That's really nice, and I guess in the end we didn't actually need this, but I feel like we do need it. Well, I will. Oops, I will keep it. Maybe like. Okay, so the assert actually doesn't go off now. Okay, I was doing something weird before then. Because I think that makes sense. Like if the polygon is defined clockwise, in the clockwise direction, then, and we remove a single vertex, it should always, regardless of how many vertices we remove, they will still be ordered in the same clockwise direction. Okay, and that seems to be correct also. Seems to be correct. So we add that assert here. Right. Oh yeah, I think most of that was because was before I checked this convexity of it, because if it is convex, then it is like counterclockwise, but we do skip that. So okay, verify clockwise winding. All right. That's very nice. Maybe I should add a reference to this nice paper that I looked at. This one was very, very, very nice. And I actually I haven't solved all problems yet. And if I add an editor, those problems will probably reveal themselves. Like if I, with my code, tried this one, right? That's not gonna work, but it should be easy to fix, I think. Right. This was a very simple algorithm, and it makes sense. But yeah, as we saw, though, the resulting triangles aren't the prettiest. They're not the prettiest. If we visualize them, like this is obviously not the best way to split up this mesh if you're looking for like some kind of regularity in the sizes of them, right? In the proportions. But it does work. So, but maybe we can find something better later. But that is nice. That is nice. That is actually, there's quite a lot of changes also, right? Like how... That's very nice. Yeah, it wasn't that much, but it's some very good progress. And I guess next time, in the next episode, I'm probably gonna add some kind of level editor, or some kind of way of like adding new points without having to do it in code, right? So that will be interesting. That will be very interesting. So let's see. We added polygons. Well, we I guess like this. Generate render and collision triangles from polygons instead of hard coding. Instead of well, it's still hard coded, right? But I don't know what to generate render and collision triangles from polygons. I guess that's good enough. Good enough. Yeah. Yep. But that is good progress. I really want to add some different type of flower also. We need some more diversity up in this game. But all right. that's it. Bye bye.